Hello everyone. So today I'm going to cover one-sided limits and continuity of functions. All right. So first we're going to start with one-sided limits. One-sided limits is a continuation of the previous topic where we describe general limits, but on this one we're really going to be focusing on one side. What does that mean? Well, means, for example, that we have a function like this. Okay, so here it is. This function will be equal to x minus 1, all right, if it's x is negative, and x plus 1 if the x is positive. So with that in mind, what we see on the graph here on figure 37 is that indeed, okay, when the function is negative, it looks like that, the arrow in red, and when the function, when my x is positive, is the one over here, the one that I have the purple arrow pointing at. All right, so from the graph we can see a couple of things. First of all, we see that this function does not have a limit on the point where x is equal to 0. And why is that? Because if we approach the function from the left, okay, from a negative number, I would get a value of -1. My limit would be -1. But if I approach the function from the right side, then my limit would be 1. So because the limit from both sides is different, then we say that there is no limit on the function. All right. So in other words, we are what we see here indeed is that for this specific point, we don't have a limit because we would get two different values if we approach the function from the left or from the right. Therefore, okay, what we see is that f cannot be close to a single number L, okay, like we learned in the previous lesson, and no matter how close my x gets to that 0, because there's never going to be one value alone that will express that approximation. Now, but okay, and this is the part, if we restrict my x to be greater than 0, in other words to the right of 0, then we see that f of x can be made as close to 1 as we please by taking x sufficiently close to 0. What does that mean? It means that if we just approach the function from the right hand side, then I would find a limit. If I ignore the left hand side, if I just approach from the right hand side, then I would get a value. I would get the value of 1. So in this situation, obviously for this situation alone, it would be the value of 1. Okay, so we can say, and we call this the right hand limit of my function f as x approaches 0 from the right is 1. And we would write like this. Now, if you notice, the difference that we see is that over here on the limit, I say x gets closer to 0, but then there's a positive sign on top of that 0. That positive sign means that I'm approaching the function from the right hand side. At the same time, therefore, similarly, we see that if f of x can be made as close to -1 as we please by taking x sufficiently close to, but to the left of 0. So, in other words, in this situation, we say that we have a left-hand limit of f as x approaches 0 from the left, which in this case will be -1, and we would write it like this. What does that mean? Means that I'm doing the limit, but just from the left hand side, just from the negative side in this case. Now what we see again is that I have my x approximating 0, but then there's a negative sign on top of that 0. So that means that I'm doing a left side limit. Now these ones that I teach you, we call them one-sided limits, and we call them because we calculate them only from one side. So, more generally, we have the following information here for you, okay? This is a quick summary of what I said so far. So the function that is right-hand side limit will have a value L as x approaches a from the right. And we would write that as the box that you see over there in red. Now, if the values of f of x can be made as close to L as we please by taking x sufficiently close to but not equal to a, then we say that we have a limit indeed. At the same time, we can say we have the same thing but for the left side, but in this case I substituted the letter for an m. Okay, so this is basically what it means to have one-sided limits. It means that we are approaching a specific value of x but only from one side rather than both, as we saw before. Okay, now we have this theorem 3 that we have related to limits. Basically tells me that if we have a function f, let f be a function that is defined for all values of x that are close to a specific point of x equals a, with the possible exception of a itself. So we would say that the limit, all right, the limit of f of x when x approximates a is equal to L if and only if both limits, okay, both the right-hand side limit that is inside the red box, if the right-hand side limit and if the left-hand side limit, okay, which is in green here, are both equal to the same value of L, which in this case will be L here in the yellow box. Okay, so the two side limits exist only and only if one sided limit exists and are equal. All right, so to illustrate this, I'm just going to do another quick example here. Now I'm going to have here a function of f and a function of g. Okay, my function of f is equal to minus x if my x's are negative or equal to 0, and it will be equal to square root of x if my x is positive. On the other side, we have the function g, where my function will be minus 1 if my x is negative and 1 if my x is above or equal to 0. So for this exercise, I want to show that the limit when x approximates 0 of my function f of x exists by studying the one-sided limits of x as they approximate the value x equals 0. And then I also want to show that the limit of my function g when x approximates 0 does not exist. So let's start with function f. All right, so for that we have that indeed for any negative number of x equal negative or equal to 0, we're going to have that the limit, okay, I'm doing this part right now in red, the limit when x approximates 0 from the negative side, that's why you see there the minus of x, will be equal, all right, and I just substituted the formula with minus x, because when the x is negative I have to use minus x. So if I substitute my x by 0, I get 0, and therefore we found the left side limit right there on that arrow. Now I'm just going to use orange for the next one. Now when my x is bigger than 0, greater than 0, then we find that my positive side or my right hand side limit, instead of substituting my f of x with a negative x, I have to substitute it with square root of x. Okay, now when I substitute the x again by 0, what we find is that it's also 0. So what we see here, we see that those two over here, okay, those two are both equal to 0, therefore they are equal, and I see that I do have a limit on this function f, So the limit, because both limits from both sides are equal to 0, then I can define that the limit of the function itself at that point will also be 0. And actually I put here in figure 38a how the graph would look like. Now for the second part, what we see is that we have two different functions. All right, so when I do my limit when g of g when x approximates from the left hand side, it will be -1, but when it approximates from the right hand side, it will actually be 1. I just substituted the functions. And now what we see here is actually that since both sides, the value from negative side and the value from the positive side are indeed different, and therefore I do not have a limit for this function at that point. All right, now I'm going to talk about continuous functions. All right, continuous functions are a property of limits to describe functions. So let's get right into it. So a function is continuous at a point. Okay, and now we're going to talk about at a specific point. So we say that a function is continuous at a point if the graph of that function at that point does not have any holes or any gaps or any jumps or any breaks. In other words, if at that point, okay, it's a line that you could just draw with just putting the pen down and you draw it without having to lift it. Okay, so for example, here we have an example of a graph, and for example, the graph of the function f is described over here. So what we can see is that, for example, the graph of this function is not continuous at the point x equal a, all right, x equal b, x equals c, and x equal d. All right, and why is that? Because indeed there are gaps. If you notice, for a there's a hole there, for b there's also a hole there, okay, at the graph. For c there is a jump or a gap, and for d same thing. Okay, now notice though, oops, let me just erase this part over here to make it better look. All right, notice though that, for example, at point A the function is not defined, at point D the function is not defined. In other words, there's not a value for that function at that point, but at point B it is defined, and I'm going to show that. You see, if at point B it's defined over here, and at point C it's defined over here. I'm circling them in blue. So having the value for the function is not the same thing as being actually continuous. So if we take a closer look at the behavior of that, we saw that at A, B, C, and D, first note that f is not defined at the A, like I said, and at A, the domain of the function, therefore, resulting in a whole in the whole graph. And we also observe that the value of f at B, okay, is not equal to the limit of the function as x approximates B, resulting in that jump, okay, resulting in the fact that at B, the function was defined up top. So the function f does not also have a limit at C, since the left hand and right hand side of them are not equal. Okay, we also saw that at point D there was no limit because there was a break in the graph, and this means that the function, this kind of function, when there is a hole or a gap or a jump like that, we call them discontinuous. All right, discontinuous at each of those numbers, but it is continuous everywhere else. So the function can be continuous and discontinuous. Okay, in this case, it's discontinuous at the points that I showed you because the limits were not equal to the value of the graph, but everywhere else it is continuous. So continuity of a function at a number, okay, and here we're talking about at specific numbers. What does it mean? A function is continuous at a number x equal a if, okay, the following conditions are all satisfied. In a first condition, the function needs to be defined at that point. Second condition, the limit of the function at that point must exist. And third condition, the limit of the function and the value of the function at that point must be equal. So a function f is continuous at the point x equal a if the limit of a at x equal a exists and it has a value of f of a. So geometrically, in other words, in the graph, f will be continuous, okay, if at the proximity of the value you want to know, it implies that there is indeed approximation between the function and the value itself. In other words, if the value or if the graph continues as a line rather than have some kind of interruption. Okay, so what will happen is if f is not continuous at a point like x equal a, then the function is said to be discontinuous at x equal a. But if the function is continuous on a specific interval, if, okay, f is continuous at every number in that interval. So now here I'm incorporating, or I'm introducing the fact that a function can be continuous in an interval. And to be continuous in an interval, then needs to be continuous in all the numbers within that interval. So for example, here what we see in this function, I have here a function, a figure 40, and I describe a continuous function between the point A and B. And I know that is continuous because I can go through the entire, if I was tracing the graph with a pen, I could trace the graph from point A to point B without having to actually lift my pen. And that would be the meaning of being continuous. Now, here I place many examples for you. Okay, to be honest, I'm not going to cover all of them in this video. I'm just going to cover a couple of them. Let's start with the first one. For example, I want to find the values of x for which each function is continuous. So what I did is actually I placed all of them here on a graph, and what I see, for example, in point 1, in graph 1, I see that all the points, okay, the entire function is defined, and therefore I could say that this function is continuous. At point B, it's exactly a very similar function. As you can see, there's a difference, which is at one specific point the function is not defined. There's a hole. Therefore, this function would not be continuous. Okay, function C, all right, also has a hole, even though that is defined down there, but it's therefore non-continuous. Function D, okay, what you see is that you have indeed a jump from the function and therefore not continuous. And again, the same thing happens at function E. So the only function here we have that is actually continuous would be A. Okay, so the function is continuous, I place there. The function A is continuous because all the conditions satisfy all values of x, and for all the others you can check on the PowerPoint, or you can quickly pause the video to read, but it's basically the same things that I just said. And here it's for function D and for function E. Now, in terms of properties of a continuous function, all right, so let's get into it. So for this kind of function, the following properties of continuous function follow directly from the definition of continuity and corresponding properties of limit. So a continuous function will have 6 different properties. Property number 1, the constant function for example, if you have a function f of x equals a specific number, all right, let's imagine, oh, f of x equals 5, okay? Whenever you have a function like that, where it's all equal to a specific constant, that function is continuous everywhere, okay? If you have the identity function, we call it, the identity function is the function f of x equal x. This one is also continuous everywhere. But now when we have, for example, situations, all right, if f and g are continuous at x equal a, in other words, if you have two different functions and both of them are continuous at a specific point, then we can also learn a couple things. And the first one is, if you pick the function f and power to a certain number n, then it will still be continuous at the point x equal a. So if you have the function f plus or minus g, and if both of them are continuous at the point x equal a, then the sum or the subtraction of them will also be equal, it also be continuous. And that rule also applies for multiplication and for division. But in division, you have to be careful to make sure that the value of g at the point a is different than 0. Then, regarding continuality of polynomial and rational functions, we already studied them before, but a polynomial function, okay, is always continuous, okay? And a rational function, when you have a function dividing by another function, is continuous in every value of x, as long as the function you have at the bottom or at the denominator is different than 0. Then once again, I put here some examples, all right, and I want to find the values of x for which the function is continuous, okay? So for example, for the first function, what we see here is that we have 3x cubed plus 2x squared minus x plus 10. Now, this is a polynomial function of degree 3, and therefore I know all polynomial functions are indeed continuous. So I immediately know this one has to be continuous. On function b and c, on the other hand, they are, as you can see, rational. So I have to be careful here. For function b, the function g is a rational function, and we need to observe that the denominator of g, in this case x squared plus 1, is never equal to 0. There is no value that you could put there that it would be ever equal to 0. So the whole function will be continuous as well. On the other hand, okay, on exercise C, okay, the function h in this case is a rational function, but in this case, however, the denominator of h can be equal to 0 at the points x equal 1 and x equal 2. So if you substitute by x1 or if you substitute by x2, then the denominator would be equal to 0. So in this case, I factored it so that you can see here are the roots, okay, and we therefore conclude that my function h is continuous everywhere except at the points x equal 1 and x equal 2. At these 2 points, the function would be discontinuous. Right? Now, we're going to talk about the concept of intermediate value theorem. Intermediate value theorem. So, the intermediate value theorem, okay, states the following. If a function f is a continuous function on a closed interval between a number a and b, and m is any number between f and a and f of b, then there must be at least one number, a number c, within the interval ab, where my function has to take the value of m. What does that mean? Okay, it means, for example, what you see here in figure 45 on part A. Now let's imagine my f of a here is a 1, and that my f of b is a 5. Now let's imagine that my m over here, I want my m to be a 3. I'm looking for a value where my function will take the value of 3. So I know one thing. If at point A, my function is 1, and at point B, my function is 5, and I know the function is continuous, there has to be at least one number. There has to be at least one number where my function would get the value of 3. In situation A, I indeed have one value like that. As you can see, I circled it, that's the spot. But I said at least one, because there are situations where indeed you can have more than one. For example, look at situation B. At situation B, I actually have three x's where the 3 of them would give me a value of m at the end. So the next theorem is the immediate consequence of the intermediate value theorem. And this is called, it not only tells us where a zero of a function f can be, exists, but it also provides the basis for a method of approximating and trying to find that zero. We call this the existence of zeros in a continuous function. So what it tells us is this: if I have a function f that is continuous on a closed interval between a and b, and f of a and f of b have opposite signs, okay, in other words, one is positive, the other one is negative, then there is at least one solution for the equation where I would get a zero. So once again, we see in the first example over here, we have one situation. Here I have f of a is positive over here, f of b is negative over there in red, and I see that indeed there is a zero in blue, okay, over there. There's 1, 0, but I can have more. If you notice on the right-hand side graph, there is actually two values where my function can get a 0. So this is the same as the one before, but it's a specific one. It's to actually define that there are zeros in a function. So geometrically, this properly states that if the graph of a continuous function goes from above the x-axis to below the x-axis or vice versa, in other words, if it goes from the negative side of y's to the positive side of y's, or from the positive side of y's to the negative side of y's, therefore it is necessarily true that the function has to have a 0 like we saw before. All right. So this is not necessarily true, though, if a function is discontinuous. And on the graph over here, you can see, for example, f of a is negative, f of b is positive. But I can only make the conclusion that there is a 0 if indeed the function is continuous. Because if it's discontinuous, I can have a situation like this, where I go from here at the bottom to the top by jumping and therefore never crossing the 0. And therefore, in this situation over here, my function, as you can see, would not have any 0. Okay, so here's another example. Okay, I have a polynomial function x squared plus x plus 1, and I want to show that this function is continuous for all values of x, but I also want to compute, okay, the value for x minus 1 and the value for 1, and I want to use the results to deduce that there must be at least one number, a value c, where in this interval I would get a 0. So starting with the first one, I see that it's a function polynomial 3, and therefore is continuous everywhere. Polynomial functions, remember, are always continuous. So to prove it, I just have to say that a function is polynomial. For point B, though, what I did was I just went to the function and I first substituted by the value minus 1, and I got a value of y equal minus 1, and then I substituted for the value of x equal 1, and I got a value of y equals 3. Now what I see is that the first one is negative, the second one is positive, and I know from the previous point they are continuous. So since they have opposite signs, theorem 5 tells me that there must be at least one number between those two where my function would have a 0. Now, if I have another, and as you can see here, I have my function once again, x cubed plus x minus 1. Right? And since the function therefore is polynomial, it is continuous everywhere, and I observe that in this case, for example, I can actually track it down better. And now, for example, if I do the function for value 0, I get minus 1. If I do for 1, I get 1. So theorem 5 also grants me that indeed there must be at least one root or one 0 between the interval 0 and 1. Okay, we can also locate the root more precisely by using theorem 5, for example, and now by trying to reduce the interval. Okay, and for example, I substituted now, okay, by the midpoint. So between 0 and 1, the midpoint is 0.5. So I go, and what I did is I substituted by 0.5, and I got the value negative 0.375. So now, because this value is below 0, and I know that f of 1 is above 0, therefore with theorem 5, now I know that my 0 has to lie between 0.5 and 1. So what did I do? With every step, what I'm doing is to reduce the interval and getting a more and more precise value or interval of where my 0 is located. Okay, I could repeat this process, all right, and do again for the midpoint, okay, and I get my midpoint would be 0.75. I go again, I substitute, and I get 0.7019. Okay. But in this case now, because my f of 0.5 is negative, but my f of 0.75 is positive, then the theorem 5 once again tells us that it has to be between these two values. So if you keep going like this, step by step of reducing and reducing and reducing, you're going to get to the point by stage 9, you get to this interval. And as you can see, this is already very precise. Okay, so this allows me, for example, when I cannot find the roots of something, this allows me to track down. Because, for example, it's very hard to find the roots of a polynomial function of degree 3. But with this method, you can easily find it. So on table 3, indeed, we see that the root is approximate 0.68 and it's accurate to 2 decimal places. By continuing the process through a sufficient number of steps, we can also obtain a more accurate or an approximation of the root as we please. Just the last point, the fact that indeed the process of finding the root for x equals 0 that we used in this process, okay, is not, like I said, it's kind of crude. But what we call, there's a name for this, we call it the method of bisection, okay? And like I said, it's crude, but it is effective, and it's a great way to finding the zeros when you don't remember the formula or when you don't have a formula to find it. And with that, we finish the video for this section. I hope you enjoyed it, okay? And if you have any questions, don't hesitate to contact me or leave a comment on the video. Thank you very much, and I'll see you next time.